Hey class, so today's lesson is going to be going over some of the special types of linear systems. So two equations that don't necessarily just intersect at one point, but some of them have all solutions and some have no solutions, and I'm going to go over that with you today. So everything we've talked about so far has always had one solution. Okay. Now, one solution, what that means is that those two lines, those two equations of lines that we're working with are intersecting. So they intersect at one point, and that one point that they intersect is the one solution. So on a graph, right, it would kind of look like this if we had a line that, goes up here, and then if we had another line that came down here, okay? So if we have these two lines, this point of intersection here is the one solution. That's the x and the y that we normally would get. Okay? But there's a couple other special cases that you might also see. Alright, so that's called consistent independent. That's the normal one. Consistent dependent means that there's all solutions. Okay, so that actually means that we are drawing the same line. The two equations are the same exact line. Okay, so all solutions would look kind of like this on a graph. Okay, it's going to be both of our equations, when you graph them, are going to be the exact same line drawn. Okay, that's why any one of these points on that line is a solution. So all solutions for all x's and all y's, the equation is true. Okay, and lastly, an inconsistent system of equations is one that has no solutions. Okay, what this is going to be, it's going to look like parallel lines instead of same line or intersecting ones. So this third option here, if we have this line and this line, okay, they're never going to touch each other, right? Because they never touch each other, they never intersect, there's going to be no solutions at all to them. Okay, so that's for parallel lines. So those are three types of linear systems: consistent independent, consistent dependent, and inconsistent. Let me show you how this works through examples. This first one I'll solve by graphing. Okay, so we can kind of see graphically what's going on here. We've got these two equations. We just want to solve this system of equations. So just like we've done with all the graphing ones, we need to write both of these equations in y equals mx plus b form so we can graph them. So we have 2x minus 3y equals 6. To get into y equals mx plus b form, we got to solve for y, so get y by itself. Alright, in order to do that, we'll subtract the 2x from both sides. We'll have negative 3y equals negative 2x plus 6. And then we'll divide by negative 3 to both sides to get y equals 2/3 x minus 2. Okay, then we can graph that part. Alright, I'll do that one in red. Okay, so you go down 2 and then do the slope. So up 2 to the right 3. And we can connect. Just like that. Okay, now the second equation is 2x equals 3y minus 4. 2x equals 3y minus 4. Once again, we need to solve for y so we can graph it. Okay, so in order to do that, we're going to get the y to the, subtract the y over to the left side, subtract the 2x to the right side. So we have negative 3y equals negative 2x minus 4. And finally, you divide by negative 3 to get y by itself. So y equals 2/3 x plus 4/3. Okay, and we can graph this one in blue. Alright, so we got to start up at 4/3, which is just above 1. Right, it's 1 1/3. And we're going to go up 2 to the right 3. And then we can connect them. Okay, so you see these lines and you realize that they are the same line. One way to check this is to notice that they're always going to have the same slope. You see 2/3 is the slope for one line and 2/3 is the slope for the other line. So if they have the same slope, they're either going to be parallel or they're going to be the same line. Okay, so since these are parallel, the answer to this one is no solutions. Okay. And the second one down here. We can also solve these through substitution and elimination like we've done a lot of times already. Okay, so how we work with this one, since the y is already by itself here, of course you could graph it if you're interested in doing that, but since the y is already by itself, what I'm going to do is I'm going to take this y stuff and I'm going to plug it into the other equation, substitute it in for y. Okay, remember substituting in for y means you take the y out and replace the y with 2x minus 4. Okay, replace the y with 2x minus 4. You don't just add it next to the 2y minus, or next to the y. So with this equation, we'll have 4x minus 2 times parentheses 2x minus 4 equals 8. Okay, now we could simplify and solve this for x. So we have 4x minus, when we distribute, minus 4x plus 8. Remember, the whole negative 2 has to be your distributive. That's why negative 2 times negative 4 is positive 8, equals 8. Right? Our 4x minus 4x cancel each other out. It's going to be 0. So we're just left with 8 equals 8. Okay, now we get back to this idea of whether or not a statement's true. So remember back a couple chapters ago we talked about no solutions and all solutions. Remember, all solutions is when all the variables cancel out, whatever is left is true, then it's all solutions. If it's false, it is no solutions. Well, ask yourself this, does 8 equal 8? Yes, it does. So that means it's all solutions. Okay, so what that actually means is that these two equations are actually the same line, just written differently. One more example. Okay, for this one, elimination looks easiest because look at the left side of the equation, it's the exact same thing. Okay, but since we have 9x and 9x, right, we need to subtract them from each other. So we're going to subtract this whole second equation from the first one. Remember, the negative has to be distributed everywhere. So that's got to be negative, that's got to be negative, that's got to be negative. All right, so 9x minus 9x is 0. Negative 5y minus negative 5y is the same as negative 5y plus 5y, which is, again, 0. And 12 minus 8 is 4. Okay, so now what we're left with, all our variables are gone, and we're left with 0 equals 4. Well, is that true? It's not true. Since that's not true, the answer is going to be no solutions. Oh, that's not how you spell solutions. Solutions. Okay. All right, and finally, another way to think about this is whether or not these two equations are written the same way. Okay, if you look at these two equations that are here, you might notice that there is a connection between these two equations. If you were trying to do elimination, okay, you would multiply this top equation by 2, right? Well, if you do that, it's going to become negative 6x plus 10y equals 12. Okay, and this bottom equation is written as 6x minus 10y equals negative 12. Well, maybe at this point you might realize that these are the exact same equations, except that one of them is multiplied by negative 1. Okay, so that makes them the exact same. You can continue this on to get do your elimination to try to solve for x and y. We just add straight down, negative 6x plus 6x equals 0, 10y minus 10y is 0, and 12 minus 12 is 0. Oh, that's not supposed to be a 10, it's supposed to be a 0. Okay, so we have 0 equals 0. Was that a true statement? It is a true statement. Remember, if it's true, then the answer is all solutions. Okay, work with these special equations, and I'll see you in class.